Hey guys, this is a new topic, computation complexity. Let's see what is its location in the big picture of the course. We have seen this big picture a lot since the beginning of the semester. We know that we have four branches for the computer science. Formal languages and automata is something that we talked a lot so far. And also we talked briefly about the computability. And in this lecture, our job is to talk about the complexity. So far, we didn't care about the efficiency. Yeah, many times I said, especially when we were talking about the non-deterministic machines, we said, oh, we don't care how many processes would be initiated, 1, 2, 5 millions. Yeah, but in reality, in the real world, this is not the case. We do care about the resources that we are consuming. We do care about the how many processes are created or how much memory we are using. All right. In fact, it is the most essential thing in the computer science that we care about the resources. All right. So in this lecture, we're gonna deal, a little bit or briefly about this concern, and the algorithm course is the place that they need to talk in details about this concern. Okay. So based on this preface, what is the objective of this lecture? In this lecture, here are some essential questions we are going to ask and answer. If we say computation A is more complex than computation B, really, what do we mean? What criteria we are measuring this? To compare two things, we would need a criteria. What is that criteria? Computation A is more complex than computation B. What does it mean? All right. And the second concern in this lecture is, can we classify the problems based on their complexity? Yeah, of course we can. So this is another concern that we will discuss in this lecture. And also, if we can do that, what classes of the complexities do we have? Which are very important things, and every computer scientist should know about that. All right. So let's start with the first question. What do we mean when we say computation A is more complex than computation B? So, yeah, briefly we answered to this before. And in summary, we can say computation A needs more resources. The resources of the computer are the amount of the resources that we need to compute something is the best criteria for measuring the complexity. Okay, so here is the conclusion of our discussion so far. Computation complexity or efficiency is the same thing. Yeah, is proportional to the amount of required resources. Okay, now naturally you can ask, resources, what are these resources? Yeah, that's a good question. So the resources that we are familiar so far in computer science. So one of them is time, how much time we would need to process a problem, right? How much space or storage we would need, how, number of the CPUs, how many CPUs we would need, how much energy we would need, how much bandwidth of the network do we need, and etc., 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 right? We can mention a lot of resources, but the point is that time and space are usually our main concern. All right. We can talk about two type of the complexities. First, time complexity, and second, space complexity, right? Because we said these two resources are more important than the others. for now, let's say. Okay, but on the other hand, space, actually storage or space is getting cheaper and cheaper, but time, no, time is always a goal. All right. So in this lecture, we mostly focus on the time complexity, and for the space complexity analysis, it's very similar to the time complexity, but we leave it for algorithm course. Okay, now let's see what is time complexity. We need to talk about two things here. First, we need to talk about what is time here and what is complexity. So probably you're thinking, okay, I know what the time is. Really? Okay, let's deal with that. So what is time complexity and what is time here? Should we answer this question? Should we measure the computation in hours, minutes, seconds? Is it meaningful to say computation A takes 2 hours? Just think about that. If we use the regular and conventional time that we know, what would happen? Definitely no, it's not a good idea. Why? Because then I would ask, okay, what was your machine? How many CPU you had? How much RAM you had? If I want to repeat your experience, then I need to prepare exactly the same computer. Yeah. So it means that we need to remove this dependency of time, the concept of time to the physical machine. Let me ask this question again. What is computation time? You recall that when we start processing a string, machine start from an initial state and it continue going to the other states and the other states again and again until it halts in a state, and that state can be a accepting state or it can be just a regular state because it depends on the string is accepted or rejected. And if we show this process as a one-dimensional projection technique, we have such thing. It starts from Q0 and it goes to another one until it halts here. And why we are saying it halts here? Because we know if the machine does not halt, we don't have any computation. Okay? So here is the definition. The best way to define the computation time would be in actually in standard Turing machine, which is a single process machine. So the number of the transitions is a very good criteria for computation time. If this process takes, let's say, n transition from Q0 until the Qn, then we would say the number of transitions is the computation time. So we would say this computation takes n. It means that n transition, of course. So if I ask this smart question, what is the computation time when the machine gets stuck in an infinite loop? What you would say? Is it infinite transition? No, there is no computation time here because there is no computation, as we said. When the machine gets stuck in an infinite loop, there is no computation, so we don't need to talk about its time. Okay, so this was the meaning of the computation time for a standard Turing machine, which is a single process machine. Now let's talk about what is the computation time of non-deterministic Turing machine. Okay, just recall that what was non-deterministic machine? If a machine is non-deterministic, it is actually a collection of single processes. So non-deterministic Turing machine is a collection of a standard Turing machine, right? And you know that all of those processes are working concurrently. right? If we show all of these processes by using a one-dimensional projection and we put all of them in one tree that we call it process tree, yeah, we would have a better picture about how to define the computation time of non-deterministic Turing machine. So look at this. So the machine starts from the Q0, and all of these are the processes, right? And some of them, let's say, stop here, some of them stop here, and some of them goes up to here, and this is one that it's it finishes here. And just imagine that all of them are working concurrently. So how can I define the computation time for this? Definitely you would say, okay, so the longest one. Yeah, you're right. So the longest one would be the computation time for non-deterministic Turing machines. In fact, the definition would be the computation time would be the depth of that process's tree. Okay, now we want to represent the time complexity. But before that, let's have a very quick review what we got so far. So we learned that complexity is proportional to the amount of the resource. And then we said time is the important resource. And also we learned the meaning of the time for deterministic and non-deterministic machines. Now our job is how can we represent this time complexity? To understand this representation, we would need some background. One of them is the concept of growth rate, and the other one is asymptotic notation, which we call it big O. Let's start with the growth rate. What is the growth rate? So we said that we care about how much resources we would need for a computation, but how fast it grows when we increase the input size. So if we increase the size of the input, which in our course it was the size of the string, how fast the resources will be increased. This rate is called growth rate. So if I ask, we need to have the slower rate or faster rate, which one is desired? Definitely the slower rate is more desired because we don't want to lose our resources very quickly. Okay, now let's be more precise about this growth rate. Let's say we have a deterministic Turing machine, a machine. Let's say it's a automata, and we put a string here, and the machine accept or reject, right? Let's define the computation time by f of n. So this machine needs f of n, and this n is actually this, the size of the string. Let me ask this smart question to make sure that you understand what this f of n is. Okay, so how it looks like for different type of machines. So for example, if this deterministic automata is a DFA, how this Fn looks like? If you said it's a linear, yeah, you are right. F of n is equal to n, which is a linear relationship. Why is that a linear? Because if you have a string, let's say 3, the size of the string is 3, you would need 3 transitions. If it is 5, you would need 5 transitions. DFA is a specific machine that the consumption of the resources is linear, right? How about if it is a Turing machine? Now it's different because Turing machine has the ability to move the cursor left or right, and that's why for the same size of the input, we might have different time. So here is an example. For example, if we input AAA, maybe the Turing machine takes 3 transitions to process that. But if we put ABA, it takes 5. So f of 3 is not a constant number for Turing machine as it was for the DFA. So which one should we take for f of 3? Yeah, let's take the worst one, which is the biggest one. So f of 3 will be 5 for this particular example. How about f of 4? Yeah, we need to calculate that again for f of 4, for f of 5, and so forth. And if we do this for different number of the input size, we might get a graph like this. Is this a good graph? What graph is this? Right. It's an unknown graph. We don't know this. We don't know its behavior. So when we say it's unknown, what do we mean? Yeah, because we have known some good graphs like this since we were in the high school. For example, n square, n cube, and log of n, 2 out to the n, and there are more. So these are the known functions that we love them because we know how they behave. What can we do now? Now we have a very, ugly graph like this. How about to approximate it with a known one? That's what we do. We want to approximate this graph with a known one. Let's say this is a known function, t of n. Okay. This approximation, if it is a valid approximation, both of them should have the same growth rate, but not totally. As you see, for example, from this point, before this point, they don't have a good behavior, but after this point, they look like they have the same growth rate, right? We are looking for a function like t of n who has the same growth rate at least from a point afterward, like this. So if this is the case, then we would say, okay, t of n is a good approximation for f of n. And then we will define a new notation that we call it big O notation. If we can find that t of n, the same growth rate of f of n, almost the same, we can approximate f of n by t of n. And to show this approximation, we use this notation, which we call it big O. So this O coming from the order of magnitude. And actually in math, the growth rate also is called order of the function. Let's be a little bit more precise. So what this t of n needs to have if we can use this notation for that. In other words, it does not matter that, let's say, this is that ugly function. It doesn't need to have the t of n. I am saying that it doesn't need to be here. If it is here, but it has the same growth rate, then it works here. So we can approximate this t of n here with this, unknown function. So I would say that it does not need to be bigger than this. So if it is here, it is okay. So in other words, if we multiply this t of n by a constant c, and the result of this multiplication will be a good upper bound for the growth rate of the f of n. So just remember that when we have a graph here and when we multiply this by a positive number, it jumps here. And if we multiply it by a negative number, it jumps here. It means that we can control where this graph goes by choosing the right constant number. You should be very careful about this equal sign. This is not a regular equal sign. It is an asymptotic notation. This asymptotic actually is a fancy word for this approximation. This big O has its own algebra, and you should be careful about that, even though it's not part of this course, but I would like to mention very quickly some of them. For example, if big O of f of n is equal to big O of t of n, it means that both f of n and t of n have the same growth rate. They grow similar to each other. And if we have a constant c here, this is a constant, and if we add this with t of n, we can eliminate this c, it doesn't matter. And if even we multiply the t of n by c, we can eliminate that as well. So in other words, for example, big O of, let's say, 2 plus x squared is equal to big O of x squared, or even big O of 5x squared is equal to big O of x squared. Based on the definition that we gave you, these make sense. Also, if big O of t of n is greater than big O of k of n, then if you add them, you can eliminate this k of n because that bigger one is important one. And also, if you have this relationship, f of n is equal to big O of t of n and g of n is equal to this guy, then if you add f of n and g of n, then the big O of, big O notation will be adding these two guys. And for multiplication, the same, but we multiply them. Please remember that this is just an FYI here, and it's not part of this course. Okay, another very quick thing, how can we prove that two functions have the same growth rate? You need to solve this limit in calculus. So if the result of this limit is a constant, then it means that t of n and f of n have the same growth rate. If the result is 0, it means that f of n grows faster, and if it is positive infinite, then it means that t of n grows faster. Okay, I put together some known functions growth rate in this table. Constant function n square, n cube, and 2 to the n. And here is the input size. And just let's focus on this, when the size is 100, if it is a constant, it's always is constant. If it is linear, it grows the same rate, 100, 100, and 10,000, 1 million, and we will compute this later. So these are, to have a feeling about how the function grows when we grow the input size. And in the next slide, we will have some graphs. So this is a constant log n, n log n square, n cube, 2 to the n, and n factorial. So you see that how bad are these two guys. They grow very fast when we increase, very small changes in the input size. It will show itself, a big number for these two. We will be talking about these 2 to the n in a few minutes. Let's move on. So how can we compare the complexity of to computation? So it has been proven that we should, first of all, we should quantify the complexities, and big O notation, as we noticed so far, is a very good choice for quantifying the complexity of the computation. So let me take an example here. For example, if we have two problem A and B, and problem A needs big O of n square resources, and the problem B needs a big O of n resources, then which one is the more complex? Definitely you would say big O of n square. So problem A is more complex because its requirement, its resource requirement is growing faster. So it means that it is more complex. Now we want to classify the problems based on their complexity. Okay, so what's the goal of this classification? We want to have a, engineering feeling about the problems. When we see a problem, we should be able to decide what kind of complexity it has, and it gives us an engineering feeling how to deal with that problem. Okay, so we can solve problems with a standard Turing machine and also non-deterministic Turing machine. Okay, because these two are two different things. So let's start with deterministic or standard Turing machine, and then we will talk about the non-deterministic one. So here are assumption. First of all, the Turing machine that I am going to use is a single tape, and also we always are interested in the worst case because this is the maximum resources that we need to pay. So these two are assumptions. Okay, so our first class is called d time n. What is this d time n? We put all of the problems that has the complexity of big O of n in this class. And this D is coming from the deterministic Turing machine, and this n is coming from this big O of n. Now let's see what kind of problems we can put here in this class. The first example is a very familiar linear search. So let's say we have an unsorted list and we are looking for a key, right? Let's call it L search or linear search. Okay, so what is the worst case for this problem? Definitely you would say, yeah, we would need n comparison, right? So we should compare this k with x1, x2, and the worst case would be big O of n, right? So we would need n comparison, so that would be big O of n. This is the first problem that we put here because its complexity is big O of n, okay? Let me explain a very briefly about these comparisons and this big O of n. If every comparison needs k, let's say it is a constant amount of time, whatever the time is, if it is k, then the total time would be k multiplied by n, right? Big O of k n. But we just said that if we have, if we multiply a constant by n, we can eliminate that. So big O of kn is equal to big O of n. Let me take another example. So how about this language? What is the complexity of this, if we want to process and accept this language, what would be the complexity of that? We have a to the n b, so it means that overall we have n plus one symbol, and for every symbol we would need one transition. Just imagine that it's a DFA, right? So we would need n plus one transition. So the complexity will be big O of n plus one, but again the constant can be eliminated, so the complexity is big O of n. So this is another problem that we can put it in our class, class d time n, right? We can put other ones, for example, a, b, n, a, and so forth, right? b to the 3n, and if n is even. We are familiar with all of these problems, and we know that based on the definition that we learned so far, all of them would need big O of n, right? Let me take other more complex examples. Look at these languages, a to the n, b to the n. How much time do we need for processing this? You remember when we used a Turing machine to solve this problem, we go back and forth to match one A one with one B, and yeah. So if you add all of those transitions, we're not gonna go in detail, but if you add all of those back and forth that we did, it would be n square, right? And the same thing, it's almost the same thing for the WWR and WW. So it means that d time n is not enough. So we would need more classes, right? So definitely we would need a new class for n square. Okay, let's create that here. So we already have the time n, and we put these problems here. Now we created a new one, d time n square, and all of those problems goes here. Okay, so far so good. Yeah, we can continue and extend this idea. So we need n cube, and probably the best example would be handling a matrix multiplication. It needs cube. So we put the matrix multiplication here, and we can continue this, right? We can continue this for big O of n to the 4, to the 5, and in general n to the k. But you know what? This kind of classification is useless. So it's not a practical thing. We don't get any practical benefit from this. We usually in practice define a very general class, and we put all of them in one class. If the time complexity is a polynomial, big O of n of k, then we put all of them in one class and we call it class P. So what is the definition of class P? Class P is the set of problems that can be decided in polynomial time by a deterministic Turing machine. So in other words, we create this class P here and we put all of those problems here. We call this class P. Actually, the class P is a very popular name, but there are two more important names for them. One is the easy problems and tractable problems, and you need to know both, all these three by heart. But you might ask why we are calling this easy. Yeah, I will explain that in a few minutes. Okay, now let's talk about exponential time algorithm. First, we need to find at least one problem that is exponential. And let me take an example in the next slide. There is a very famous problem that we call it SAT, or satisfiability problem. I explain it through an example. So let's say we have a logical expression like this, and the question is, for what values of these three variables we have, P, Q, and R, for what values of P, Q, R, this expression will be satisfied. When we say satisfied, it means that the value of the expression will be true. Okay, how can we solve this problem? Probably you are thinking the best way is to create a truth table for these three variables, And so we have three variables. The truth table will have 2 to the 3 or 8 rows, and for each row we put the values of the PQR in this expression and see which one makes this expression as a true statement. That's a very good strategy and a very good solution. Let me show you in the next slide that how it works. So this is the truth table, and for the first row we have PQR, all of them are true. So we put true here and see how it works. When we calculate this, we will get F. So this is not a solution for this expression, right? We try the next one. Oh, okay, this makes this expression as a true, so this is a solution. If P is equal to T, Q is equal to T, and R equal to F, this will be a solution for this expression. And we can continue all of this, right? After that, we can pick which one is the solution. What happened here? We had to investigate row by rows, and this is called exhaustive algorithm. When you had to check all of the possibilities from A to Z, then it is called exhaustive algorithm. So this satisfiability problem or SAT is the algorithm that we proposed. So first construct the truth tables based on the n variables, and then evaluate each row, and then pick those that make the expression as a true. Theoretically, we offered an algorithm for this problem, so theoretically it's computable. But now let's talk about its efficiency, right? What is the efficiency? Since we have 2 to the n in general, 2 to the n rows, so it means that, let's say, every row we would need k time for processing each row. In other words, overall we will have k multiplied 2 to the n, the total time to process this table. So the complexity will be big O of k multiplied to the n. But we say the k is a constant, and we can remove that, so it will be big O of 2 to the n. So this is the complexity of this problem. So now let's talk about its advantages and disadvantages. Let's a little bit dig into this, how horrible or how good this algorithm is. Is it a practical algorithm? Is it a good thing or not? To understand this, let me take an example for when we have 100 variables, which is a very practical thing in the real world. So if we have 100 variable, the size of the table will be 2 to the 100, right? And do you know how big is this number and how much time a computer needs to process all of these rows, right? 1 hour, 2 hour, 1 day, 1 week, how much? So it depends on the computer that we are going to use, right? So let me take a practical example to give you a feeling about these kind of problems with exponential complexity. Let's say we have 100 variables, so 2 to the 100 rows, and we have a computer, a very, very, very good computer that can process 10 to the 9 rows in just 1 second. Now, if I ask you, how long does it take if this very powerful computer wants to process all of these 2 to the 100 rows, what would you say? Yeah, just you can pause the video and try to think about that. Okay, now let me answer to this question. So 2 to the 100 is, we don't have any feeling about this kind of numbers, let me first convert this 2 to the 100 to a base 10. Usually we use this approximation. 2 to the 10 is equivalent to 1024, which is approximated with 10 to the 3. So it's equal to 1000. If we approximate 2 to the 10 to the 10 to the 3, then 2 to the 100, we can write it like this, and then we can approximate 2 to the 10 with 10 to the 3, and it will be equal to 10 to the 30. So we have this much rows. Okay, now let's see, convert 1 year to, let's see how many seconds we have in 1 year, right? So 1 year, it is 365 day, and it is 24 hours, and each hour is 3600 seconds. And if we calculate this, it would be 3.2 multiplied by 10 to the 7. So each year is this much seconds. And since our computer can process 10 to the 9 rows in 1 second, so in 1 year, this computer can process 10 to the 7 multiplied by 10 to the 9. It is equal to 3.2 10 to the 16, right? So this computer can handle or process this much rows per 1 year. So rows per year, right? So how many rows we have? 10 to the 30. So if we divide this 10 to the 30 over 3.2 multiplied by 10 to the 16, we will get 3.2 multiplied by actually 3, almost 3 multiplied by 10 to the 13 years. And I'm sure that most of you are shocked. Yeah, you are right. 3 and 13, 0 in front of that, years it took to process this much rows. And just consider that we are using a very powerful machine. 10 to the 9 rows per second is a huge number, right? You see how horrible is this exponential algorithm. I put here an exercise for this guy. And if you remember when I was talking about the grammars, this was one of those grammars, complexity, and I said, okay, we will get back to this. And so I put it here for your exercises based on the how we calculated the complexity for the satisfiability problem. You can do the same thing. And here we are using the same computer, and the length of the string is 50. Just put the 50 here. So the big O of, number of the production rule is 1, 2, 3, 4. It is 4. And here we have 50. It will be 101. Yeah, just try to calculate what number is this. Okay. Now, based on our knowledge right now, just try to imagine that. So if we have 100, the input size is 100, just look at this and this. So just compare these two. If we have an algorithm who is in cube, and big O of n cube, right? It takes 1 million, whatever it is, right? But if the algorithm is exponential, it takes that big number that you just saw. So if we have 1 million record, and if we use the same computer, it will be processed less than 1 second, right? But if we use another algorithm which is exponential, it takes centuries and centuries and centuries. Yeah, just I put it here to show you how horrible is this exponential algorithms. Now let's turn to the non-deterministic Turing machines. Let's see when we use non-deterministic Turing machine how the problems change. So here we have a theorem that says if a deterministic Turing machine solve a problem in an exponential time like this, the same problem will be solved by non-deterministic Turing machine in a polynomial time. So using a non-deterministic Turing machine changes the complexity from exponential time to a polynomial time. So that's a huge difference, right? So let me take an example here. For example, this SAT problem complexity was this. If we use a deterministic Turing machine, but if we use the same problem with non-deterministic Turing machine, the complexity will be n to the p. P is a constant, whatever it is. It doesn't matter. It's. So it's a huge difference, right? Between this exponential that now we have a very good feeling about that and a polynomial time. Based on this theorem, we created a new class and we called it NP. And this NP class is the set of those problems that can be decided or solved in polynomial time, but by using non-deterministic Turing machine. So this N is coming from that non-deterministic, and this P is coming from that polynomial time. So these problems are also called hard problem or intractable problem. You remember that I said we will get back to you that easy guy. So class P is called easy, and now you understand why we call it easy and why we are calling this NP class as a hard. So because these hard problems is the exponential guys, and the exponential guys timing, you saw that by that example, right? Okay, what is the relationship between the class P and class NP? Can we say that if a problem is here, it can be solved by deterministic Turing machine in polynomial time, but the same problem can be solved by non-deterministic Turing machine in polynomial time too, right? So these are the problems that are in common between the NP and P class. But if we have a problem here, it can be solved by non-deterministic Turing machine in polynomial time, but the same problem, if we want to use a deterministic Turing machine, then we need to pay an exponential times like this, right? You agree that these class P problems is a subset of the NP problems, right? So here is the relationship that we have. So P is a subset of NP. Okay, so computer scientists found some polynomial time for the P problems as we know, and like multiplication, and they have found some exponential time algorithm for some other problems like SAT or SAT here. We have similar problems like Hamilton path, and I didn't mention that, but they are very famous and you can search for them. Or pcrack or password cracking, finding the prime numbers. But we were so lucky that in some cases, specifically like finding the prime numbers and checking the prime numbers, in 2004, these three guys found a polynomial time algorithm. So it was here before, but then we move this from here to here. So now the question is, and this is an open question, a very important question, is this possible that we find a polynomial time for the other problems as well? Or in other words, can we assume one day in near future that all of these problems from NP goes to P? In that case, then P will be equal to NP. So far, nobody could answer this question. So we don't have any yes and we don't have any no for this question. Yeah, it's an unknown question and it's open. And if you solve that, you can get $1 million. Just go here in this website and redeem your $1 million. That's it, guys. We are done. Yeah, I hope you enjoyed the course and I really wish you all the best in your career.